This video introduces our research to develop computational human phantoms for radiation protection and medical applications at Hanyang University Radiation Engineering Laboratory. First, I would like to briefly introduce the computational human phantom. The computational human phantom is a virtual digital human model used for computer simulations and analysis. This slide shows a voxel-type computational phantom which is most popular these days. As you can see here, the voxel phantom is composed of a huge number of voxels with their ID numbers. Each ID numbers represent corresponding organs in human body. For example, these ID numbers in this sliced image represent skin, lungs, heart, bone, and other organs. After placing voxels of all sliced images in 3D space, a computational human model is finally constructed. Computational human phantoms are mainly used in radiation protection and medical applications. For radiation protection applications, computational phantoms can be used to evaluate radiation risk to human body by external or internal exposures, as well as radiation dose reconstruction for nuclear accidents such as Fukushima nuclear power plant accident. For medical applications, computational phantoms are used for treatment planning and plan verification in radiation therapy. In addition, they are used in medical imaging research. In the early stage, computational phantoms are represented by simple shape geometry such as spheres and cylinders. Current voxel phantoms can represent more anatomical realism than the early models. International Commission on Radiological Protection also uses voxel phantoms as ICRP reference phantoms. However, voxel phantoms have limitations to represent organ shapes because organs are represented by voxels with limited size. We can see that the skin voxel model has large holes. In order to address limitations of the voxel phantoms, we constructed polygonal mesh surface phantom by converting voxel phantoms to polygonal mesh surfaces, which are widely used in 3D computer graphics. Let me explain the conversion procedure. The primitive polygonal model is constructed from voxel model using 3D rendering technique. However, the primitive polygonal model has bumpy surfaces because of the remaining of stair-stepped voxel model during the rendering procedure. So, we refined the primitive model by smoothing surfaces, minimizing the number of facets, and finally adjusting the organ volume to match original mass values. This is the result of converted polygonal mesh model. As you can see, polygonal mesh skin model can represent thin structure of real skin without any holes. Next, we can see the constructed internal organs as polygonal models. As like skin models, wall organs also represent well their thin wall structure without any problems. In the case of small and large intestines, due to their complex shapes, it was impossible to construct polygonal models using the aforementioned method. Therefore, 3D contouring and NURBS modeling method were used for them. This is the completed polygonal mesh surface phantom. In contrast with conventional voxel phantoms, it is possible to represent thin or complex organs as like their real structure. Especially the constructed surface phantom is more meaningful than other surface phantoms in that it can be directly implemented in a Monte Carlo code without use of the conventional voxelization method. In addition, we are converting polygonal mesh surface phantom to tetrahedral mesh geometry for representation of density distribution in the organs. As you can see, the inner space of polygonal models can be divided into many tetrahedrons without geometry distortion. This is the completed tetrahedral mesh phantom. Its external shape is identical to the original shape of polygonal mesh phantom. At the same time, it is possible to represent density variation by using the structure of the tetrahedral meshes. Based on these techniques, recently we have developed new mesh-type ICRP reference computational phantoms which are also called MRCP for short, to address limitations of the currently used voxel-type ICRP reference phantoms by converting the voxel phantoms into a high-quality mesh format. Through the conversion project, the internal organs in voxel format were converted to those in high-quality mesh format with more realistic shape, and complex organs and micron-thick radiosensitive layers were defined in the phantoms. This slide shows the MRCP for adult male and related numerical information. Similarly, this slide shows the MRCP for adult female and related numerical information. One of the major advantages of the MRCP over the previous voxel phantom is that they can be flexibly deformed into specific postures and body shapes according to certain exposed individuals. These are the mesh-type reference phantoms deformed into different postures. The next figures are adult male phantoms with various body shapes and female phantoms with various body shapes. We are also developing 4D computational human phantom, which can be used for medical applications. On the contrary to radiation protection field that usually consider the average organ dose, the main concern in the field of radiation therapy is a dose distribution on a patient. Also, with the development of radiation treatment technologies such as IMRT with dynamic MLC, proton scanning therapy, or therapies with the consideration of respiratory motion, the need for upgrade patient dose calculation technique became very important. To meet the need, we are developing 4D computational human phantom for medical applications that can accurately calculate the patient dose by realistically simulating the radiation therapy. Computational human phantom for medical applications requires some special concerns. It should be based on patient-specific data so that it can represent patient's unique anatomy and motion accurately. In addition, since those simulations should be performed to multiple patients, the procedures for the generation of phantom and dose calculation should not be overly time-consuming. However, currently available 4D phantoms do not satisfy these requirements. 4D MCAT, NCAT, and XCAT phantoms cannot represent patient-specific anatomy, so it cannot be used for patient dose calculation. The time-dependent voxel phantom that generated based on patient 4D CT can represent patient-specific anatomy, but the respiratory motion is discrete because of the limited number of phases, and it may cause some error on dose calculation. Hence, we developed two types of phantom that feature patient-specific anatomy and continuous respiratory motion: 4D tetrahedral phantom and 4D voxel phantom. The continuous deformation of a phantom is composed of following steps. First, the information on patient-specific anatomy and motion is obtained from 4D CT. In this step, several additional phases are generated between existing phases for the better description of gradual and continuous motion. Then, we can calculate the motion of the organ in the form of deformation vector field by applying deformable image registration on each phase images of 4D CT. By applying the calculate DVF gradually, we can make several additional phases so that the continuous motion is represented. The dose calculation with Monte Carlo simulation and developed phantom is also conducted in 4D. When a radiation interacts and deposits some energy to deforming phantom, the deposited energy is moved to corresponding position of the reference phase and cumulated. With this real-time dose registration technique, which is called energy transfer method, we can accurately calculate the dose distribution in moving phantom geometry and dynamic treatment beam condition. This is the continuously deforming 4D tetrahedral phantom we developed by applying continuous deformation technique and 4D Monte Carlo simulation technique. You can see the radiation is transported while the patient organ in tetrahedral geometry is deformed continuously. This is the first 4D tetrahedral phantom in the world. This is the continuously deforming 4D voxel phantom. The radiation is transported while the phantom deformed according to the patient's respiration, and the dose is registered in real time. Since this 40 voxel phantom is automatically generated from 40 CT and the computational speed is fast, it is expected to be directly applied to clinic without additional investment on computation resources. In conclusion, our group are developing advanced type of computational human phantoms such as polygonal mesh surface phantom, tetrahedral mesh phantom, and 40 phantom beyond the current voxel phantom technology. Based on our advanced type phantom developing technology in the future, we will be able to do real-time 4D Monte Carlo dose calculation while a computational human phantom moves following the movement of the human body.
Hey, sexy lady. Oppan Gangnam Style.
Thank you for your attention.